Hello. I'd like to take a minute just to talk about what we know so far about functions and also then talk about where we're going with the idea of a function. So what we know so far is that functions come in a bunch of different varieties. We have mappings. This is a visual way that we can represent a function. We can take that mapping and convert it to a table of values. Another way that we have a function. We can take that table of values and we can convert that to a set of ordered pairs. And then finally, we can take a set of ordered pairs and we can plot these points on a graph. Now, each of these represents 4 different functions. And I want you to take a moment to look at each of them, study them, and make sure you understand why each one of these is a function. And if you can't answer that question, why it is a function, then I need you to be asking some more questions or set up an appointment to meet with me. The other thing we know about functions is that we can name these functions, and popular names for functions are f, g, and h. And when we see that function notation, it looks like multiplication. It looks like f times x or g times x. But what we know is that math notation is not that good. And because of that, it has nothing to do with multiplication. F is simply the name of the function, and x is the input variable. And the way we would read these functions is f of x, g of x, and h of x. Now, one common misconception we have about functions, especially as you look at the graphs here, is people think that sometimes a function must have a pattern to it. But that's not necessarily the case. We can see in this graph of the green points that this represents a function because every value of x maps exactly to one value of y. So even though there's no pattern to this, it still is considered a function. But what happens when functions do have patterns? Well, that's a pretty special situation. And so we can see that when we plot points on a graph, sometimes patterns will appear. Here's a pattern right here that's developing, and we call this a quadratic function because every input maps to exactly one output, and it has a pattern that is a parabola. And so when we see these parabolas, we call these quadratics. Here's another pattern. This pattern is called a periodic function because it fluctuates up and down, and then eventually it comes back to its starting point. So these are special types of functions as well, called periodic functions. A lot of times we use trigonometry, like sine, cosine, and tangent, to represent these types of periodic functions. The function we're going to be studying next is what we call a linear function. Now, these linear functions simply just make a straight line, but it is a pattern nonetheless. And so we're going to be talking about how do we define the relationship between the input and the output in these linear functions, or even the quadratic functions or the periodic functions. And this is where your equations come in. So in a quadratic function, it might be very easy to think of f of x as equaling x squared. And when we have this relationship between inputs and outputs, we get that parabola-shaped graph. Or in a periodic function, we might have g of x equals sine of x. And that creates that periodic table or periodic pattern. And then in a linear function, this is probably where you're most familiar with slope-intercept form, where we have something like 4x minus 7. So as a matter of fact, I'm going to tell you the code word to move on to the next section of the Google form is the words linear function. All lowercase, one space between the word linear and function. Linear function is the code word.